All right, folks, we're going to get started here in Chapter 3. Starting off, we're going to look at something that's called the derivative, and the derivative as a function. So I'm what I'm doing here is I'm combining sections 3.1 and 3.2 together into one video. Section 3.1 is, it's basically just a brief introduction to the concept known as the derivative. So let's get started. What we're going to do at this time, folks, we're going to develop and introduce one of the most important definitions in mathematics. It's the definition of the derivative. Now, up to this point in time in your mathematics career, you have studied a rate of change. The only rate of change that you have seen has been the average rate of change. And hopefully you were told this when you were learning it. In other words, whenever you use the slope formula to find the slope of a line through 2 points, that slope formula and slope of a line through 2 points was actually computing an average rate of change. So hopefully you heard that way back when you first learned the slope formula and you were computing the slope of a line through 2 points. I just want to do a very brief comparing and contrasting of an average rate of change, something you already know, versus what's called an instantaneous rate of change. An average rate of change, well, that's analogous. You could think of as like an average velocity. For example, if I told you, that from my house to the Ohio State University campus, where I normally park for, home football games. If I told you that I usually make that trip in about 2.5 hours, and it's a total of, 168 miles, you could compute my average velocity for the trip. You could take 168 miles, divide it by 2.5 hours, and you would get my average velocity for the trip to be 67.2 miles per hour. That's my average velocity for the trip. I am not pulling out of my driveway at 67.2 miles per hour, nor am I pulling into my parking spot at the Ohio State University campus at 67.2 miles per hour. It's just an average. We compare that to something that's called an instantaneous velocity. An instantaneous velocity would be your velocity at a specific point in time. So, for example, if you've ever received a speeding ticket and you got pulled over for speeding and you were informed that it was determined by radar. Well, that radar gun was computing your instantaneous velocity. It was computing your velocity at a particular point in time. The average rate of change concept is given by the slope of a line. Now, specifically, it's given by slope of a secant line. A secant line is nothing more than a line that passes through 2 points on a curve. The instantaneous velocity, or instantaneous rate of change, is given by the slope of a tangent line. The slope of a tangent line is a line, well, a tangent line is nothing more than a line that passes through a single point on the curve. A little bonus information here. The word secant, it actually comes from the Latin word secare, which the Latin word secare literally means to cut in two. The word tangent, it comes from the Latin word tangere, and its literal translation means to touch. So let's try to ease into this whole concept by considering it's a pretty friendly function, f of x equals x squared. In part A, let's determine the slope of the secant line, which I'll denote as m sub sec, that goes through the points 1, 1, and 3, 9. So, there's a graph. The blue graph is the graph of x squared, and I've drawn in the secant line that is going through the points 1, 1, and 3, 9. Then in part B, we're going to try to determine the slope of the tangent line, which I'll denote as m sub tan, at the point 1, 1. So there's the graph of the function and the graph of the tangent line. So part A, we're finding the average rate of change of the function x squared on the interval 1 to 3. In part B, we're finding the instantaneous rate of change of the function at the point 1, 1. And in order to do this, in order to do parts A and B, I'm going to head off to the chalkboard to work through it. So get this written down. Really important topic that we're discussing here. And I'm heading off to the chalkboard. All right, folks, this example, we looked at the function f of x equals x squared. Part A was to find the slope of the secant line through the points 1, 1, and 3, 9. And on the previous slide, we had a graph of f of x equals x squared, and I had drawn in the secant line. Part B, we're going to try to estimate the slope of the tangent line at 1, 1. And on the previous slide, I had a graph of the function x squared, and I sketched in the tangent line. So let's do it. So part A, slope of a secant line, is just slope of a line through 2 points. Those were 2 points on the curve of f of x equals x squared. So we know how to find slope of a line. We know slope, and I'll use the m sub sec because it's secant line slope. We know that it's a change in y over change in x. You know the slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So it's a 9 minus 1 over 3 minus 1. So that's 8 over 2. So that's 4. And in fact, in this table over here, I could fill that in. Notice I made a table for x, f of x, and then the third column is the slope of the secant line through x, f of x, and 1, 1. So x is 3, f of x is 9. The slope of the secant line through 3, 9, and 1, 1, we just computed that to be 4. Now this table's going to come in handy as we try to do part B. Because what I'm going to do, we know now the slope of a secant line. I'm going to try to find the slope of another secant line, but I'm going to let that point get closer, the second point, I'm going to let it get closer to the point 1, 1. I mean, we started off, we were at the point 3, 9. Now I'm going to try to get closer to the point 1, 1. In fact, here was the graph of x squared. And here's that point 1, 1 that we're trying to get the tangent line slope up. So here's 3, 9. We just found the slope of that secant line. I'm going to pick a point that's even closer to 1, 1. Let's go to an x value of 2. So I'm coming here to this x value. That'd be the point 2, 4. Now I'm going to find the slope of the secant line through the points 2, 4 and 1, 1. Well, we know the slope of the secant line that goes through the point 2, 4 and 1, 1. It's change in y over change in x. So 4 minus 1 over 2 minus 1, it's 3. Could I find a second point that's even closer to that point 1, 1? Of course I could. I could come to, let's say, an x value of 1.5. Then f of x is, 1.5 squared, which, that's a 2.25. So now think about what's happening here. I've now come to this point right here. It has an x value of 1.5, a y value of 2.25. And I'm going to find the slope of the secant line through those 2 points. I think the slope of the secant line through those 2 points will be an actual better approximation to this tangent line slope than what it was through the points 1124 or 1139. I think as I get points closer and closer and closer to the point of tangency, 1, 1, I think as I get a second point that's closer and closer and closer, I think those secant line slopes will get closer and closer and closer to the tangent line slope. But let's find the slope of the secant line. So if I do my change in y over change in x, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, I would get the slope of that secant line to be 2.5. Could I get a point that's even closer to 1, 1 than 1.5, 2.25? And of course I could. I could let x be 1.1. And the y value, 1.1 squared, is 1.21. Now, I'm going to have a hard time sketching this or drawing this, in the small figure I have here because, an x value of 1.1 is going to be really, really close to that point. But I have two distinct points that I can find the slope of the secant line through. Find the slope of the secant line through 1.1, 1.21, and 1, 1. So we use the slope formula. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And we'd get the slope of that secant line to be 2.1. Now I have just enough room to ask you, could I get even closer? Of course I could. I could have an x value of 1.01. That's pretty close to the x value of 1. And if x is 1.01, f of x, well, 1.01 squared is 1.0201. So I find the slope of the line through 1.01, 1.0201, and 1, 1, change in y over change in x, and I get the slope of that secant line to be 2.01. Of course I could get even closer, but let's see if we can answer the question. Can we guess what the slope of the tangent line at 1, 1 is? I mean, as we picked our second point to get progressively closer to the point of tangency, 1, 1. These points are getting progressively closer to the point 1, 1. It looks like the secant line slope was getting progressively closer to 2. So I'm going to make a guess. I'm going to make a guess that I believe the slope of the tangent line at 1, 1 is 2, based on that table that we just did. Let's head back to the slides and see where this takes us. All right, folks. Hopefully what we saw was apparent in the prior example was that to estimate the slope of the tangent line, we let our second point get closer and closer and closer to the point of tangency 1, 1. And by letting that second point get closer and closer and closer to the point of tangency 1, 1, we were actually employing the limit process. We were letting the distance between our point of tangency 1, 1 and the second point get smaller and smaller. So to go further with this, to really generalize the process we did in that introductory example, I'm going to head back to the chalkboard to generalize the process. All right, we went back to the slides, and I said I hope you saw the limit process in that first example we did, but we're going to head back to the chalkboard to generalize it. So let's try to generalize what we really did in that first example. So first off, here's the sketch of some function. Don't know what the function is, I don't care. I've arbitrarily found some value a. The coordinates of that point are a, f of a. I'm coming over here to the right, some arbitrary distance. I don't know what the distance is. I don't know how far it is. So let me just generically say that is a distance of h units. Well, if I'm starting at A and I move to the right h units, that should drop me off at A plus h. So let's find the coordinates of that point. We know this point has an x-coordinate of A plus h. Its y-coordinate would be found by evaluating the function at A plus h. And the only way I have of representing that is the y-coordinate is found by evaluating the function f of A plus h. So the secant line that goes through those 2 points, we know the slope of the secant line through those 2 points would be, well, we use our slope formula. F of A plus h minus f of A, y2 minus y1, y sub 2 minus y sub 1, over x sub 2 minus x sub 1. Now notice that immediately simplifies. Notice that denominator immediately simplifies to just an h, which makes sense. That's the change in x, is h. So let me put this in a little box, and I'm going to say that probably looks familiar to you. You should have seen something similar to this in college algebra. It actually had a name. It was called the difference quotient. Okay, so our task, what we're looking at, how do we find the slope of a tangent line? Well, in that example we just did, we had a point of tangency, I believe it was 1, 1. We picked secant points that got progressively closer to the point of tangency. So think about this. As these points are getting closer and closer to the point of tangency, that means the value of h would be getting smaller and smaller and smaller. In fact, h is approaching nothing. H is approaching 0. So I'm going to write that down. To get the slope of the tangent line, tangent at the point A, f of A, we just simply let h approach 0. That's the limit concept, and that gives us the following. The slope of the tangent line equals the limit as h approaches 0, f of A plus h minus f of A all over h. So basically the slope of the tangent line is nothing more than the difference quotient with a little limit statement in front of it. So let me put that in a box, and let's head back to the slides to see how we are going to continue this. All right, after we did that generalization, we now know that to get the slope of a tangent line, m sub tan, at any point A, f of A, we simply need to do the following. The slope of the tangent line is equal to, the limit as h approaches 0, f of A plus h minus f of A, all of that over h. So let's practice this. Let's practice this in an example. So in this example, in part A, we're going to determine the slope of the line tangent to the graph of f of x equals x squared at 1, 1. We already have an idea of what the slope is. We've estimated it. Now we're going to actually determine it by using this formula we have at the top of the slide. Then in part B, let's determine the slope of the line tangent to the graph of f of x equals x squared at 3, 9. So I'm off to the chalkboard to work through these. Make sure you have this written down because here I go. All right, hey, this example had two parts. In part A, we're going to find the slope of the line tangent to the graph of f of x equals x squared at 1, 1. This was the first example we did, and for making a table and a chart, we believe that the answer here is 2. But now we can show if it really is 2. So, here's how I would get started. The slope of the tangent line equals the limit as h approaches 0, and it's f of a plus h. Well, there's my a value, so let me just write that in. Instead of a plus h, let me write 1 plus h minus f of a all over h. So this is the limit as h approaches 0. Okay, now we have to evaluate the function at 1 plus h. Well, remember you put 1 plus h in for x, so you have a 1 plus h quantity squared minus f of 1, so put 1 in for x. 1 squared is 1. Now we have just a little bit of algebra to do. We have to take 1 plus h and FOIL that out, so 1 plus h times 1 plus h is a 1 plus a 2h plus an h squared. Then we combine like terms, and in the numerator you see the 1's cancel out. So we're left with just a 2h plus h squared. And, it's still indeterminate form 0 over 0, but hopefully you're saying, well, in the numerator you could factor out an h. So we factor an h out of the numerator, leaves us with a h times 2 plus h. And then since we could factor it out, we can cancel it out. That gives us the limit as h approaches 0 of 2 plus h. We substitute, and we get this to be 2. So our guess was correct. But this is the real deal. This isn't a guess. This is how we know the slope of the line tangent to x squared at 1, 1. We know it is definitely 2. Alright, so now in part B, we're going to determine the slope of the line tangent to the graph of f of x equals x squared at the point 3, 9. In fact, here's what I want you to do. I'd like you to pause the video, and I'd like you to do part B and see what you get. Once you've done part B, restart the video. It should look very similar to what we did in part A, but restart the video and we'll see if you have the correct answer. Alright, part B, slope of the tangent line. So slope of the tangent line equals the limit as h approaches 0, f of a plus h, here a is 3, so I'll put that in 3 plus h, minus the f of 3, all over h. Well, that equals the limit as h approaches 0. We have to evaluate our function at 3 plus h, so 3 plus h goes in for x. So we have 3 plus h quantity squared minus, well, f of 3 is 9. So we have to do a little bit of algebra. Just like we did in part A, we have to FOIL out 3 plus h. So 3 plus h times 3 plus h is a 9 plus a 6h plus an h squared. And then don't forget the minus 9. Combine like terms in the numerator, and it looks like the 9's cancel out. So we're left with the 6h plus h squared over h. And then in the numerator, well, we better factor out an h. That leaves us with h times 6 plus h. And since we factored it out, we can cancel out the h's. So that gives us the limit as h approaches 0 of 6 plus h. Now we substitute and we get 6. So the slope of the line tangent to the graph of f of x equals x squared at 3, 9, the slope of that tangent line is 6. Let's head back to the slides and see what's brewing. All right, folks, hopefully we saw it's not too bad to get the slope of a tangent line. You know, we could continue this. We could find the slope of a tangent line to that function x squared at different values of x. You know, we could find the slope of the tangent line to f of x equals x squared at x equals 4, at x equals -1, at x equals 23, at x equals pi, at x equals -13, etc., etc., etc. But the last two examples indicate there may be a better way. In other words, it would be nice if we could go through that process that we did in the last example. If we could just go through that process only one time, and then given any value of x, like x is 4 or -1 or 23, etc., we could quickly determine the slope of the tangent line. So we are now going to look at how to do just that. We are going to look at going through the process only once that will determine a little formula. And this little formula will give the slope of the tangent line for any value of x. Once we know this little formula, we'll be able to quickly state the tangent slope for any value of x. So let's make a quick trip back to the board to see how this is done, how we can go through this process only one time. So heading back to the board, folks. All right, folks. I said we should be able to generalize what we've done from our prior two examples. The last example, I did one part, you did one part. We should be able to generalize it. So here's how we're going to generalize it. Rather than picking a specific number for A, let's make it as general as possible. Let's just pick the arbitrary x. So let me put that here, x. We know this point on the curve is x, f of x. Okay, you've got to do the same thing. If I come to the right h units, that would drop me off over here at x plus h. So this point on the curve has coordinates x plus h, f of x plus h. So the slope of the secant line that goes through those 2 points, well, the slope of the secant line is f of x plus h minus f of x over x plus h minus x, which the denominator cleans up to just a h. Then to get the slope of the tangent line at the point x f of x, so the slope of the tangent line at the point x f of x, it's the same process. We're going to let h approach 0. We're going to do the limit as h approaches 0 of f of x plus h minus f of x all over h. That's true for any x. And this is a really, this is a biggie. This is something really huge. So we're going to head back to the slides and give this a very special name in calculus and in all of mathematics. So let's head back to the slides and see what kind of name we're going to give this expression. All right, we just saw on the board, and I said that the slope of the tangent line, I said it was a biggie. I said what we did was really important. It was huge. So here it is, folks. It is the definition of this thing called the derivative. The derivative of f at x is given by, okay, that's read f prime of x. So it's given by f prime of x equals the limit as h approaches 0, f of x plus h minus f of x, all of that over h, provided the limit exists. We're going to see those are 4 pretty important words in a little bit in this section. We're going to analyze that. And before we go further, I want to give you some notes on this definition. My first note, in order for the derivative of f at x to exist, well, x has to be in the domain of the function. I mean, if x isn't in the domain, there's no way a derivative could exist. When we go through the process of computing a derivative, that process is called differentiation. We are going to say a function is differentiable at x if its derivative exists at x. And the fourth and final note, f prime of x is a function. I mean, it looks like a function. It looks like function notation. Its purpose, what it does, it gives the slope of a tangent line, which means it gives us an instantaneous rate of change. But because it is a function, that means it also has a domain. I mean, all functions have domains. Now I'd like to look quickly at some different notations for the derivative. So the first one we've seen is f prime of x. If our function was called g of x, the derivative would be g prime of x. If our function is given to us as a y equals, well, we could represent the derivative as y prime, or we could represent the derivative as dy dx. And then the fourth notation that I have listed here is df dx. I rarely, if ever, use that notation. I'm just listing it here, just in case, who knows, in the future you might see it, and I don't want you to be surprised by it. There's one more little notational thing that I do want to talk about, and it's this special notation, which is read d dx of f of x. Okay, that notation, d dx of f of x, it's used to communicate a lot of words. It's used to communicate, differentiate with respect to x, the function f of x. So rather than write down all those words, differentiate with respect to x, the function f of x, we would just simply write d dx of f of x, as I shown here. All right, time to do an example. Let's look at the function f of x equals x squared plus 3x minus 1. In part A, let's determine f prime of x, the derivative of the function. Once we know the derivative, we'll be able to do part B very quickly. We'll be able to determine the slope of a tangent line at those 6 different values of x. It'll probably take us maybe 1 second for each value of x to get the slope of a tangent line. Very quick, very efficient. Then in part C, let's kind of do an old algebra review topic. Let's get an equation of the line tangent to the graph of f at the point 1, 3. Remember, in order to write an equation of any line, you need to know the slope of the line and a point on the line. So we'll review that in part C. So folks, get this example written down because I am heading off to the chalkboard to do it. All right, folks, we just learned one of the biggest definitions in all of mathematics, the definition of the derivative. So in this example, we were given the function f of x equals x squared plus 3x minus 1. And in part A, determine the derivative. Determine f prime of x. So we know f prime of x equals the limit as h approaches 0, f of x plus h minus f of x, all over h. So that's the limit as h approaches 0. We have to evaluate the f of x plus h. So that means x plus h has to come into the function wherever there's an x. So that gives us x plus h quantity squared plus 3 times x plus h minus 1. All of that is the f of x plus h. Then we subtract f of x. And I'm going to put that inside parentheses so I don't make a careless sign mistake. All right, now we have a lot of algebra to do. So we have to take x plus h and square it. That gives us an x squared plus a 2xh plus an h squared. I would distribute the 3, 3x plus 3h minus 1. I would distribute the negative 1, so minus x squared minus 3x plus 1 all over h. And then I always say, hey, let's clean up the numerator. Let's combine any like terms that we have. So let's see, anything we can combine with this x squared. Well, we have an x squared here. Hey, look, x squared minus x squared. That's gone. So let me do that. Look at this. 3x minus 3x. That's gone. It's kind of sweet. And then a negative 1 plus 1. That's gone. So we had a lot of stuff kind of disappear. Let's see where we're at. We're at the limit as h approaches 0. Okay, we have a 2xh plus an h squared plus a 3h. Oh, that's all we have left in the numerator. How about that? We can't find the limit because we have the indeterminate form 0 over 0, but you know by now we're going to factor an h out of the numerator. So we factor an h out of the numerator. Leaves us with a 2x plus h plus 3. And once we factor it out, yeah, we can cancel it out. So we're left with the limit as h approaches 0 of 2x plus h plus 3. Substitute 0, and we get 2x plus 3. Folks, we just found the derivative of the function x squared plus 3x minus 1. We found that its derivative is 2x plus 3. Remember, derivative is telling us an instantaneous rate of change. It's telling us the slope of a tangent line tangent to any point we want on this curve, x squared plus 3x minus 1. So in part B, we should be able to answer those questions just like this. This is that little rule. This is the little formula that no matter what x is, it's telling us the slope of the tangent line. So the slope of the tangent line at x equals 1 is found by evaluating the derivative at 1. Well, here's the derivative. Evaluate the derivative at 1 and you get 5. The slope of the tangent line at 4. That's found by evaluating the derivative at 4. So evaluate the derivative at 4 and you get 11. The slope of the tangent line at negative 3. Well, that's found by evaluating the derivative at negative 3. So 2 times negative 3 plus 3. 2 times, that's negative 6 plus 3, it's negative 3. The slope of the tangent line at x equals 7. Evaluate the derivative at 7. You get 17. The slope of the tangent line when x is 1/2. Well, evaluate the derivative at 1/2. And you get 4. I mean, what's the slope of the tangent line at an x value of negative pi? Just evaluate the derivative at negative pi. And you get negative 2 pi plus 3. That is very quick and efficient to now compute slopes of tangent lines for any value of x. Oh, hey, there was a part C. I didn't get that up here on the board, so let me erase. Let's see, part C was determine an equation of the line tangent to the graph of the function at the point 1, 3. So we need to know the slope of the tangent line at 1, 3. Well, that's right here. So I'm gonna erase this. And let's see, let me write up here part of the words for part C. It was equation of the tangent line at x equals 1. Well, at x equals 1, the y coordinate is 3. All right, we know the slope of the tangent line is given by evaluating the derivative at 1, which we know is 5. So folks, I know the point of tangency. I know the slope. To get an equation of the tangent line, if I know a point and the slope, I'm going to use point-slope form of a line. Point-slope form is y minus y sub 1 equals m times x minus x sub 1. So we'd have a y minus 3 equals 5 times x minus 1. That's the equation of the tangent line. Yeah, if you want, you could distribute the 5 and then add the 3 to both sides to get it into slope-intercept form. That's if you'd want. Let's head back to the slides. You know what? Before we head back to the slides, here in section 3.2 exercises, I'd like you to do number 36 right now. So pause the video and do number 36. When you're done, restart the video. I'll be here at the board, working through it. Okay, folks, number 36, you were given the function f of x equals 5x squared minus 6x plus 1. You were also told a is 2. In part A, you were supposed to determine f prime of x. And then in part B, the equation, an equation of a tangent line at the point A, f of a. So let's focus on A first. Let's get the derivative, f prime of x. So one more time, let's write this down. F prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. So that's the limit as h approaches 0. All right, f of x plus h is 5 times x plus h quantity squared minus 6 times x plus h plus 1 minus f of x, and yeah, I'm going to put that in parentheses so I don't make a careless sign mistake. So I do my algebra. See, x plus h quantity squared, well, that's an x squared, plus a 2xh plus an h squared. Distribute the negative 6, so minus 6x minus 6h plus 1. Distribute the negative 1. And it looks like I have to distribute this 5. So let me do that. I get a 5x squared plus a 10xh plus a 5h squared. And then all this other stuff. Alright, so hopefully I have some stuff cancel out in the numerator. And I do. 5x squared minus 5x squared, gone. Negative 6x plus 6x, gone. 1 minus 1, gone. So I'm left with, in the numerator, a 10xh plus a 5h squared minus a 6h. Okay, I still can't find the limit. It's indeterminate, 0 over 0. But if you know what? I can factor an h out of the numerator. That's kind of sweet. So let's see. If I factor out an h, I'm left with a 10x plus a 5h minus 6. And then I can cancel out the h. And I'm left with the limit as h approaches 0 of 10x plus 5h minus 6. Substitute in, and I get 10x minus 6. That is f prime of x. So f prime of x equals 10x minus 6. Now we do part B. Equation of tangent line at A, f of A. So it's an equation of the tangent line at 2, f of 2. So let's see, f of 2. I have to put 2 in for the x's, evaluate f of 2. So that's 20 minus 12 plus 1. So that's 9. So we know the point of tangency is 2, 9. We just need to determine the slope of that tangent line. The slope of the tangent line for this problem is found by evaluating the derivative at 2. This x value, 2. Well, here's the derivative, f prime of x equals 10x minus 6. Evaluate that at 2. So we have what? 10 times 2, that's 20. 20 minus 6, 14. We know the point of tangency. We know the slope of the tangent line. So we will use the point slope form of a line. And we get y minus 9 equals 14 times x minus 2, which is an equation of the tangent line, but I know most of you want to distribute that 14 and then add 9 to both sides to get it into slope-intercept form. So, hey, that's it for number 36. Let's head back to the slides and see what we're going to do next in our discussion of the derivative. All right, hopefully that example, things are coming together and you were able to crank through number 36 on your own. Got another example here. We're just going to determine the derivative, f prime of x, for the function f of x equals 1 over x squared. So there's some nasty-ish type algebra here, and I thought we would take a quick look at it. So write this example down because I'm heading off to the chalkboard to do it. Hey, in this example, we're going to get the derivative f prime of x for the function f of x equals 1 over x squared. So, well, here we go. F prime of x is the limit as h approaches 0, f of x plus h, minus f of x all over h. So that's the limit as h approaches 0. Okay, f of x plus h, that's 1 over x plus h quantity squared, minus f of x, which is 1 over x squared, and then all over h. And see, next we need to determine a common denominator for the numerator. Well, that common denominator is x squared times x plus h quantity squared. Now I'm going to multiply the numerator and denominator by that least common denominator to try to get out of ugly complex fraction world. So my next step is to multiply the numerator by x squared times x plus h quantity squared, and to multiply the denominator by x squared times x plus h quantity squared. I mean, keep in mind, when I'm multiplying numerator and denominator by the same thing, I'm really multiplying by a version of 1. So let's see. In the numerator, when x squared times x plus h quantity squared gets distributed and multiplied by this fraction, well, we're just left with an x squared. When it gets multiplied here Well, we're just left with an x plus h quantity squared. And then the denominator is an h times x squared times x plus h quantity squared. And that's not too bad. I got out of complex fraction world into regular fraction world. But now I have some work to do. In the numerator, I have to FOIL out this x plus h quantity squared. So I'm going to pull that, I'm going to pull it up here. And I'm going to do that. So I have an x squared minus, and I'm going to put it in parentheses so I don't make a careless sign mistake. The denominator, I'm just going to leave it alone. Alright, now in the numerator, why don't we distribute the -1. And after we do that, I think we have something cancel out. We can combine like terms. Well, look, straight away, x squared minus x squared. It's gone. So we're left with the limit as h approaches 0 of -2xh minus h squared all over h x squared x plus h quantity squared. Still indeterminate form, 0 over 0, so in the numerator, why don't I factor out an h? So I factor an h out of the numerator, and I have a -2x minus h. And then once I factor out the h, I mean, you know the drill, I can cancel out the h. So I'm left with the limit as h approaches 0, -2x minus h over x squared times x plus h quantity squared. Now I can substitute. Substitute 0 for the h's, and I get -2x over x squared. And then 0 comes in here for the h, so x plus 0 is x. So I have another x squared. Which, that gives me a -2x over x to the 4th, which simplifies to -2 over x cubed. So for the function 1 over x squared, the derivative is -2 over x cubed. There were a lot of steps here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 steps. You know, here real soon we're going to learn how to get this derivative, the derivative for this function, in a lot fewer steps than 11 steps. But let's head back to the slides and see what's next. All right, that last example, there were a lot of steps involved in that, and what about 9 steps. It's going to be really nice here real soon when we start to learn how to quickly and efficiently compute derivatives, and we'll be able to get that derivative in like 1 step. But we're not there yet, folks. All right, in the definition of the derivative, I told you the last 4 words in the definition were really important. Remember, the last 4 words were provided the limit exists. Very important words. So let's look at this example. We're going to determine f prime of 0 for the following. In part A, the function is absolute value of x. And in part B, it's the cube root of x. So get this example written down, because I'm going to head off to the chalkboard and we're going to see why those 4 words, provided the limit exists, are really important. So here I go to the chalkboard. Hey folks, so now we're going to see why those 4 words at the end of the definition of the derivative, provided the limit exists, are really important. So here we're going to find f prime of 0 for the function f of x equals absolute value of x. And real quickly, you know what the graph of absolute value of x looks like. Something like that. So we're going to try to find f prime of 0. That point right there. So here's how I would do this. F prime of 0 is the limit as h approaches 0. I mean, we might as well go ahead and just put the 0 in for the x's. So it's f of 0 plus h minus f of 0 over h. So we have the limit as h approaches 0, just of f of h minus f of 0 over h. And we know that the f of h is found by taking h and tossing it in here. So that gives us absolute value of h. F of 0, well, we know the absolute value of 0 is 0. So this just becomes limit as h approaches 0 of absolute value of h over h. It's indeterminate form, 0 over 0. And the only way I have to try to determine the limit as h approaches 0 is to look at it as the limit as h approaches 0 from the left side of 0 of absolute value of h over h, and the limit as h approaches 0 the right side, absolute value of h over h. And here's what we need to remember. In fact, let me write it here in yellow chalk. We need to remember absolute value of x is x if x is greater than or equal to 0, and it's the opposite of x if x is less than 0. I need to remember that in doing this limit as h approaches 0 from the left side of 0. So we're over in negative number land. It's this part of the definition of absolute value that will be used. So when h approaches 0 from the left, the absolute value of h is the opposite of h. And we know that the opposite of h over h simplifies to negative 1. The limit as h approaches 0 from the left of negative 1, well, the limit of a constant is that constant. Now when h approaches 0 from the right side of 0, so we're out in positive number land, absolute value is this. So the absolute value of h will equal h because we're in positive land. So I would rewrite this. Absolute value of h is just h. We know h over h is 1. The limit as h approaches 0 of 1, well, the limit of a constant is that constant. So, I'm sorry, I left off the plus signs here, telling you from the right. So the limit as h approaches 0 from the right is 1. The limit as h approaches 0 from the left is a negative 1. It's not approaching the same value. That tells us this limit does not exist. And if this limit does not exist, that tells us f prime of 0 does not exist. That's why those 4 words are so important. F prime of 0 does not exist for absolute value of x. When we go back to the slides, we're going to talk about y. That's why I sketched the graph up here real quick. There's a graphical connection. Part B. You know what part B, let me quickly sketch the graph of cube root x. It would look something like this. So it's that point right there. So we're going to try to find f prime of 0. So we start off the same. F prime of 0 equals the limit as h approaches 0, f of 0 plus h minus f of 0 all over h. So that's the limit as h approaches 0, f of h minus f of 0. And see, f of h is the cube root of h. f of 0, well, f of 0 is 0, so we have cube root of h over h. Well, you know, I think we could simplify this. Let's see, cube root of h, I can rewrite that as h to the 1/3. And then there's an old property or an old rule of exponents that says when the bases are the same and you're dividing, you subtract the exponents. So 1/3 minus 1, 1/3 minus 1, that's negative 2/3. And an old rule of exponents that says I can rewrite h to the negative 2/3 as 1 over h to the 2/3. So the limit as h approaches 0. I'm going to let you play around with that on your own. I'm going to tell you that this limit does not exist. And because that limit does not exist, that means f prime of 0. It doesn't exist. It's not defined. And there's a graphical connection to this as well. Both of these examples illustrate the graphical connection on when a derivative does not exist. And we're going to head back to the slides, and I'm going to highlight it with both of these. And I'm also going to highlight something else when we go back to the slides. Notice, this is going to come up later on, notice that the function absolute value of x, it is continuous at x equals 0. It's continuous at x equals 0, but the derivative does not exist at x equals 0. Cube root of x, it is continuous at x equals 0, but the derivative does not exist at x equals 0. So let's head back to the slides and see, you know, the graphical connection to when a derivative does not exist. All right, in that example, we saw that the derivative didn't exist at 0 for both of those functions. And I had a quick sketch on the board of each of those functions as well. So derivative f prime of 0 did not exist for absolute value of x, nor did it exist for the cube root of x. That was because in both of those cases, in both parts of that example, the limit did not exist when we were using the definition of the derivative. That's why those 4 words were important. I did have the graphs up on the board, but now I want to kind of talk more about what that means graphically. So here's the graph of f of x equals absolute value of x. And there's the graph of f of x equals the cube root of x. Now let's look at each of those graphs at x equals 0. Okay, now notice over here on the graph of absolute value of x at x equals 0. Notice how the graph has a corner there, or we could say it's making a sharp turn at x equals 0. Notice on the graph of cube root of x over here, notice that x equals 0. If I were to draw a tangent line there, I think the tangent line would be a vertical line. And we know vertical lines have undefined slope. So what does this mean graphically? The derivative does not exist where a graph has a sharp turn or a corner, such as what we see over here on absolute value of x, or where we have a vertical tangent line, such as we see over here on the cube root of x. And the derivative is not going to exist wherever a graph is not continuous. And then I mentioned this other thing called a cusp. Some people call, if you look at the graph of square root x at x equals 0, some people call that a cusp. So I need you to remember where derivatives do not exist. It's important you remember where the graph would have a corner or a sharp turn, a vertical tangent, or it's not continuous. Those are all values of x where the derivative would not exist. Hey, a quick theorem here. If your function is differentiable at a, so the derivative does exist, then the function will be continuous at a. Another way to state this theorem is if a function is not continuous at a, then the function is not differentiable at a. Okay, folks, this is a really important distinction because what these theorems really tell us, they really tell us that being differentiable at a point means the function is continuous at that point. I've known many math professors in my time at Ohio State that just shortened that down to the phrase, differentiability implies continuity. On the other hand, being continuous at a point, that's not enough to guarantee that you're differentiable at that point. Our last example illustrated this. Both of the functions, absolute value of x and the cube root of x, both of those functions were continuous at x equals 0. But the derivative did not exist for either one of them at x equals 0. All right, we have 2 more examples we're going to do, folks. And for these final 2 examples, I'm just going to head off to the chalkboard. So I'm just going to put each example on the chalkboard and we're going to work through them. So time for me to head off to the chalkboard. All right, here's another example I wanted to look at. I said we were going to go back to the chalkboard and look at an example. The question is, where does the derivative not exist? I don't know what the function is. Don't care. That's just the graph of some function. So I want to make sure we're dialed into graphically where a derivative does not exist. So I'm looking at this graph, and at x equals -2, I see a sharp turn. Sharp turn. The derivative doesn't exist. So the derivative does not exist at x equals -2, and that's because there's a sharp turn there. The derivative does not exist at -1. The reason why it doesn't exist at -1, the function is not continuous there. Not continuous, no derivative. Oh, it looks like x equals 1. I would call that another sharp turn. So the derivative does not exist at x equals 1. Everywhere else looks fine. So at these values, these 3 values of x, the derivative does not exist. Sharp turn, not continuous, another sharp turn. Have one more example I'm going to do, so I'm going to pause the video, clean the board, and get one final example up here. Hey folks, in this example, we are going to sketch a graph of the derivative of the function that is shown in this graph over here. So this is the graph of some function. I don't know what the function is, I don't care. But we're going to sketch a possible graph for the derivative of this function. This is kind of cool. So let's see, where do we begin? Well, let's think. Derivative tells us slope of tangent lines. So the first thing that jumps out at me is that at x equals -2, at x equals, I'm going to say that's about -1/2, and at x equals 2. It looks like if I were to draw tangent lines at those 3 values of x, the tangent lines would be horizontal. Horizontal lines have a slope of 0. So at these 3 values of x, the derivative, I know the derivative is 0. Now for any value of x that's to the left of -2, any tangent line that I would draw, doesn't it look like it would have a positive slope? Let's make note of that. For x less than -2, any tangent line would have a positive slope. That means the derivative would be positive. From -2 to -1/2. So from -2 to -1/2. It looks like here any tangent line I would draw would have a negative slope. So let's make note of that. From -2 to -1/2, tangent lines would have a negative slope. So the derivative is negative. And likewise, doesn't it look like from 1/2 to 2, derivative would be positive? Tangent lines would have positive slope. So let's make a note of that. From -1/2 to 2, tangent lines would have positive slope, so the derivative would be positive. And then from 2 to infinity, it looks like any tangent line would have a negative slope. So for x values greater than 2, tangent lines would have a negative slope, so the derivative is negative. Boy, you know, there's a better way for me to condense this down. Let me show you a better way to condense this down. Let's make a number line. I know where the derivative is equal to 0, so let me put those numbers on the number line. And let's see. The derivative is, let me put an F prime right here in bookkeeping. The derivative is positive on this interval. On this interval we said it was negative. On this interval we said the derivative would be positive. Let me put those in parentheses. And out here we said the derivative would be negative. Notice how the function itself on those intervals, the function is increasing. And then on this interval the function's going down, it's decreasing. Here the function is increasing, and then out there it's decreasing. We're going to talk about this in a future chapter. It's this behavior. The derivative is positive, negative, positive, negative. That's what I need to graph. And here's how I graph that. So let's see, I'm going to put -2 here, -1/2, and 2. I know the derivative is 0 at those three values of x, so that I know the graph must have x-intercepts at those three values of x. So I know 3 points that are definitely on the graph of the derivative. Now in the interval -infinity to -2, the derivative is positive. If it's positive, that means its graph is above the x-axis. So from -infinity to -2, the graph is above the x-axis. At -2, it's going to hit the x-axis because that's where the derivative is 0. From -2 to -1/2, the derivative is negative. So from -2 to -1/2, the graph is going to be below the x-axis. But keep in mind, I have to get back to the x-axis at an x value of -1/2. So that means I'm going to go below the x-axis, and at some point I have to turn around and come back and hit the x-axis. From -1/2 to 2, the derivative is positive. So its graph has to go back above the x-axis. But I have to hit this. So that means I'm above the x-axis. At some point I have to turn and come back and hit x equals 2. And then from 2 to infinity, the derivative is negative. That means its graph is below the x-axis. There is a potential graph for the derivative of that unknown function. It takes a little bit of time. You have to do some analysis to think about it. But that's it for this video that covered, at the very beginning, a little bit of section 3.1 and section 3.2. So now you can do all the exercises that are assigned in sections 3.1 and 3.2. So head off and do all those exercises, and thanks for watching.